Well, hi everybody, and thanks for coming by for yet another demo. Um, I'm going to start this week. Prior to today, most of the demos have involved primarily showcasing language features and, piece by piece putting together this language. We're at a point now where most of the bigger features are there in some form. They're going to get refined a lot and made to work together, and maybe some things will be simplified, and maybe some features will even be dropped if they can be implemented in terms of other features. But for the most part, we've sketched out the basics of the language. And what I've been doing in the majority of my programming time lately is starting to write non-trivial sized programs in this language and using the features and seeing what's needed and seeing what's missing and catching bugs in the compiler and stuff like that. So this week I'm going to start sort of digging into the code that I've written. So today we're going to start by looking at some of that code, and then as a lead in to one or two language features. And then probably next time we'll do a comprehensive look over a full program. Maybe not. It might be too much to do in one session, but anyway, by non-trivial programs, of course, I mean games, because that's my main discipline, right? It's my problem domain. And so when I start writing a new game in this language, I of course want to make sure that some of the problems that I had writing games in C++ are solved, right? Or are easier to deal with here. And I've talked about this before, but one of the things I want to do is set up a system for entities, right? Entities are entities are stateful things in a game world. You could call them actors or objects, except the word object is kind of taken by object-orientedism, so it's hard to use it without confusing people. But you have all these things in a world, and your engine should be able to store them in a way that it's very efficient to process them, to query them in several ways, right? But it's not only should it be efficient, but it should be convenient. When I was working on The Witness, I was typing all kinds of gameplay code, and essentially most gameplay code is doing queries on entities, right? Like, oh, you stepped on this pressure plate and it's now active, so it's going to trigger things that it's connected to. So let's go query what kinds of things it was connected to, and based on what types those entities are, we'll do some effects, right? That kind of description is like 95% of gameplay code. So you want to be able to do that well, but so there's like a back end to it that you want to be efficient, and a front end that you want to be easy to use as a programmer. You don't want to have to go through all kinds of like high friction, annoying things all the time just to deal with a back end that's efficient. And that's why certain features in the language are the way they are, like recall, for example. A long time ago, I demoed this kind of thing where you can say, data structures are SOA or whatever, and that leads to a certain kind of memory layout for the structure, but at the same time, the way you logically refer to the structure doesn't change at all, right? So you have freedom to manipulate the back end of things to some degree without changing the front end of things. So let me talk specifically about a problem that I wanted to solve, right? I want to allocate these entities, and I want to be efficient about dealing with their memory. And I want good usage of the cache. If I'm iterating over, like say I want to search through all the doors in the game to find which ones have certain properties, like which ones have a certain tag on them, because I want to open all doors with a certain name tag on them, right? I want a way to traverse those doors to find the right ones. So I'm going to go off on a slight diversion here and talk about general heap allocation, which is often how things are allocated in games when people don't care that much about performance. And then I'm going to motivate what I'm doing here today, and then we'll look at the code of what I'm doing today, right? So now if you're in a language like C and you're generally allocating things on the heap, you get something kind of like this little diagram that I have here, where, you know, I've allocated some objects where the objects are this green data, right? So my game thinks of this as a 1 square big thing of green data and a 1.5 square and like a 5 square thing, right? However many bytes that is. My game said malloc or new or something, and malloc or new gave it back this green piece of memory, right? And now, if you're not thinking about performance or, well, if you're not thinking about performance, then you don't tend to think about what's behind that, right? But a generalized heap allocator is doing a bunch of stuff behind that that is often inefficient, right? So, for example, there's always some bookkeeping overhead. So note here, every time I've got a block of green, which is some memory that my application cares about, it's preceded by this block of orange, which is, you know, something that the allocator uses to organize the heap. It's how it knows how to traverse the heap and which blocks are used and which blocks are not used and all that good stuff. And this may be stored directly in the heap. It may be stored separately. I think if I was going to design a heap allocator now, I would actually store this in a separate memory array. But however you do it, it's there, right? So that's in there. If it's contiguous, it pollutes the cache a little bit. So like I said, green here is my useful memory, right? The purple here is fragmentation. So, you know, usually heaps, they try to reuse stuff. So for example, I've allocated this green bit here, and there's all this fragmentation after it, which is essentially wasted memory. And the reason why that's there is because in order to keep this heap organized, it's got some rule about how big the blocks of memory can be that it gives back to the application, right? It doesn't give you every random size because that makes it hard to reuse blocks later, right? If you allocate 17 bytes, and then it gives you exactly 17 bytes and then starts a new chunk after that, then if you free that 17 bytes and allocate 18 bytes later, it can't reuse that 17 byte chunk, right? It has to give you different memory, and then if you never allocate something 17 bytes again, then that memory is wasted forever, which is very bad behavior for an allocator, right? So these allocators tend to round up to some kind of size. And here I've used like power of 2 in terms of number of squares. So this is 1 square, this is, well, no, that's not right. This one's rounded up to 3. Anyway, there's some rule here by which these are rounded up to a bigger size, right? And so anytime you round up, you're wasting some amount of memory in there, right? So this is internal fragmentation. And the reason I say internal fragmentation, usually this is just called fragmentation, but that's because people aren't necessarily thinking about external fragmentation, which is a different thing, right? So in my allocator, like malloc or whatever, in order for it to give me memory, it has to have memory to give me, right? And the way that it gets the memory to give me is by asking for that memory from the operating system. And the operating system will tend to give you memory in big pages, right? And how big those pages are depends on your OS and your application settings, possibly. But if I'm sort of going from left to right and giving out memory, then if this whole rectangle is one big page, it's quite possible that I just don't ever use the end of the page because we never use that much memory. But that is committed to me by the operating system. So that's what we call external fragmentation. Hopefully I've got my terminal. You know, I didn't look up any of this before giving the demo, so maybe there's newfangled names that these are called. 5% chance I'm getting everything backwards or something, but as far as I know, this is what these things are called. Okay, so for a system like a game where you've got a bunch of entities, like let's say we've got 20 different types of entities, things like doors, humans, dogs, power cables, puzzle panels, right, monsters, whatever. You've got some set of those things. Usually in a static language like C++ or this language, those things will be expressed as a struct that's of a known size at compile time. And because it's a known size at compile time, you can use an allocator that takes advantage of that. And again, we've demoed this earlier in simpler application cases, right? A long time ago, I demoed, well, maybe I demoed a pool allocator. I don't know if I demoed a fixed size allocator. But anyway, down here at the bottom here is a diagram of what we're going to look at today. I call it a bucket array, right? Where you have, it's a system for allocating memory of the same size. So let's just look at this for a second, right? So dark green is things that are occupied. Light green is things that are empty because we freed them. But notice there's no fragmentation between the dark green and the light green because everything's the same size. So if you free something, you know that you'll be able to put something of the same size back later. So there's no internal fragmentation. There's no purple here. There is external fragmentation because, you know, here I've made a bucket. I'm calling this whole thing a bucket. It's like one contiguous piece of memory, and it's 6 items wide, and I'm not using the last 2. So those count as external fragmentation. And what's not even drawn here is that maybe my bucket is not as big as a memory page or something, and then you might get more external fragmentation that my application isn't even thinking about because, anyway. You know, so if your bucket is the size of a memory page that you got from the operating system, then you'll get a little bit more external fragmentation because the remainder of your page size divided by your entity size is probably not 0, right? So there's always going to be some external fragmentation in the scheme. But my thesis here, and many people's thesis here, is that external fragmentation is not as bad, because it doesn't really pollute your cache if you're iterating over items, right? So if you're iterating over a bunch of things here, you know, you're visiting all these guys, then all this extra like wasted memory is at the end all packed together. So you're going to have a minimal impact on your cache usage when you're looking at these other guys. And then here, what I drew here, you can imagine this is a bit field or something that just tells me which of these are occupied and which are not. You're always going to have some degree of bookkeeping overhead, no matter how well you hide it, right? You could even have an apparent 0 overhead here by knowing something about what your entities look like so that you can set that field to 0 if it's not being used or something, and then you search that. But that's still bookkeeping overhead because you could have compressed that out otherwise. Anyway, so this is just like a bit field with 1 bit for each of these. So it tends to be a very small amount of overhead compared to what a generalized heap would do. So then the overall layout of the system I'm trying to do, and I've demoed an entity manager earlier, but each of these things is a bucket array, like that diagram we just looked at, and there's base classes, and they're stored separately from what you would call the derived class. Or I'm using object-oriented terminology. I don't really think about it object-oriented way, but every entity in the game has sort of these base entity structs, and they're stored SOA because that helps me iterate through all of them and do queries, right? So gameplay code can run faster, or even like, you know, often the editor, you know, if you're going to pose the problem, how do I search through all the doors or even all the entities in the whole game and find the ones that obey certain properties? The answer is usually, well, build some acceleration structure for those entities or for those doors or whatever. And that's how you usually do it for, you know, spatial queries, if you're searching for something within 1 meter of a certain position or whatever. But the problem is, in a bigger game, you're going to search for so many different things that it becomes impractical to build ways of accelerating all those searches, right? And even if you did build all those, it would be just a spaghetti bug mess. It would be crazy. And it would waste a lot of memory and all kinds of stuff. So really, you would rather have, for your most important queries, you do want that kind of accelerator that helps you do things quickly. But then for everything else, you just want a general way of plowing through stuff and just brute forcing stuff and making it be fast, because then you don't have to have all these specialized code paths. So that's what I'm designing for, right? So in the editor, for example, you know, in an editor, you can even suffer little frame hitches that you would rather not have during gameplay. Like if you do certain operations, like I'm pressing a button to do something to a certain set of entities, it's a little more okay to take a frame hitch there or whatever. So rather than well, just to simplify things and let you do brute force code in that kind of case so that you can get more code done faster and it'll be less buggy, that's what this design is for. So you've got this array of entities, and this is going to be this bucket array that I'm talking about. Bucket arrays have multiple buckets. This is maybe 1 bucket, and there'll be another one and another one. The reason you have multiple buckets, I forgot to mention this. Let me go back. So like I said, you have external fragmentation here because you didn't use all the items in the bucket. But that's only for the last bucket, right? Say I start with one bucket and I'm filling it out, green, 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 and then I want to allocate another one. This bucket is full. So I'm going to allocate a new bucket, and then it's going to be all red, and I'm going to start filling it out, green, 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 and I'm going to make a new bucket. So hopefully most of my buckets are dark green. There'll be very little dark green, very little light green, and only one bucket ever should have red in it, which is sort of like the last bucket, right? Anyway, so here's a bucket with entities, and then here's a bucket with doors, which is the part of the door struct that doesn't contain the base entity, but it's got a pointer that sort of points back to this entity array. So here, this guy here is a door that has this base property, right? The base property is stuff that everything has, like position and entity ID and stuff like that, right? So here's another door, it's pointing to a different place in this array. Here's another door, it's pointing to a different place. Then we might have particle sources, right? These are bigger than doors. Note that doors are bigger than the base entity. Particle sources might be even bigger because they have all these color and timing controls on them. And so you see again, it got a little messy, so I just started drawing arrows into nowhere, but each of these has a pointer that points into the base entities, it doesn't have to be a pointer in the strict way. It has to be some way of locating the base entity, right? It could be a pointer, it could be something else. And then, you know, the rest of this is whatever data is needed. Does all of that make sense? Does anyone have questions about the motivation here? Because now we're just going to start looking at the code. So questions. I guess this is done enough that I can delete the in progress. Someone says, makes sense. That's not a question. My initial implementation of SOA was naive. I don't know. I don't know what you guys are saying. All right. So people are following along in the chat. How much, so Tyler's asking how much CPU overhead was there in the witness, just considering game logic stuff. There was a lot initially because I was just randomly heap allocating everything. I was doing what you would do in C++. I was just saying like new door, right, and new dog. And that puts stuff randomly on the heap. So if you're going to iterate over all the doors, you're going back and forth randomly along the heap, right? And that's no good. And at some point, I kind of fixed that a little bit, but still, you know, by allocating stuff generally in order, yeah, but then things would get out of order a little bit as you manipulated entities, and it was less good. But it was significant. Like definitely, the biggest problem in the witness was doing save games, right? Which on the PC it was fine. So every minute or so we decide if we want to autosave you, right? And to do that, we scan through all the entities in the world and diff them against the base state to see if there's something we should save, which in principle is very robust. The thing is, there's over 60,000 entities in the witness, right? So you can do some very simple optimizations, like mark constant things as constant, so you don't check them. So like collision volumes that aren't ever mounted on anything that moves are constant. And that's really a lot of entities. But on consoles, which have slower, consoles tend to be more slowed down by your program waiting on memory, right? So that kind of access pattern was very bad, and we were taking frame hitches when it was time to do save games on a console. So we had to do just crazy complicated stuff to optimize the autosave, for example. And then all kinds of other times I was worried about gameplay code. Like there's probably gameplay code that causes frame hitches on console when you solve puzzles or open doors or something. And we just don't even have full stock of what it is because there's so many different cases. Like if you think of all the different little things that happen in the witness. Like at a big level, the witness is a lot of similar things, but all those similar things are kind of different in terms of what the code actually needs to say. And there's enough cases there that we couldn't even, with a team of our size, systematically benchmark them all. So it's one of those cases where your code morale gets a little poor. You're just like, I'm sure some of this is too slow, but I can't worry about it right now because we're shipping. And so you want to get out of that trap as much as you can. Someone's asking, does blending SOA and non-SOA structs mess up how the memory is packed? It doesn't really make a lot of sense, I don't think. Either an array of something is SOA or it's not. You can't have an array of both. If you're talking about different arrays, it doesn't matter, right? In fact, you might have different arrays where some things are SOA and some are not. Anyway, let's move on and talk about the specific code that we're doing. So this is a bucket array, right? And just like last time, it's a struct that takes a type parameter and a value parameter, right? So we've got the type of the thing that we're allocating, which will be an entity or a human or something, and how many items per bucket. And this is a parameter that we tune, right? So we want this number to be high enough that our allocations are very efficient and we're not calling the base allocator all the time, right? So right now, this just gets its buckets from malloc or the equivalent, right? Or the operating system allocator maybe, right? So you don't want to call back to that allocator very often. So you want this number to be high, but you also want this number to be low in order to keep down external fragmentation. So you can make the trade-off of how many items you want in a bucket, and you can change that for any particular entity type, right? So if you've got a bucket for humans and you know there aren't that many humans in your game, you might set this to like 10, right? But if it's like the witness and there's 20,000 collision volumes, then you might set this to, 2,000 or something, right? And then you only take ever 10 mallocs to allocate all 20,000 of your collision volumes. And your external fragmentation is less than or equal to size of 2,000 times the size of the collision volume, right? And you can, depending on what numbers are acceptable to you, you turn that up and down, right? So anyway, there's an allocator that you can override what we use. We talked about that before a long time ago. We're defining this type. So just like last week with the hash table, we're defining a custom type called myBucket. And so this thing is just going to have an array of buckets. And each bucket also wants to know the type and the items per bucket. So we're basically baking a struct down here. And these parameters here are going to be the same as these parameters here, right? And then we've got two arrays. These are dynamic arrays, right? And this is all the buckets we ever allocate, so that we can iterate over the buckets and find things in them or visit everything that we've ever allocated, right? And all the buckets that are not full, right? And when we want to allocate a new thing, we just look at the first bucket in the unfull buckets. We find the first slot in it that's not full. We fill that slot, and then if that bucket is full, we take it out of unfull buckets. So allocation should be very fast usually, right? And then if unfull buckets ever becomes empty, then we call the base allocator to make a new bucket. And that's all there is to this. Aside from all that, behaves like, we want this to behave like an array. I don't have operator overloading yet, so I don't have subscript defined on this, but we have other interesting things, which we'll see. So I'm going to run pretty fast through the implementation of this, because if you program a lot, you know how this goes, right? Anyway, so I've got, just like with the hash table last time, I've got this occupancy mask where I know which buckets are occupied. And then I've got, the data, which is, this is just exactly, this is of the type that's passed in, right? So this is an array of whatever type that we're allocating, entity or whatever. And we're saying explicitly this is uninitialized because we don't want to spend any time zeroing it out. This is initialized, so this starts as 0, right? And then every bucket has a bucket index, which I believe we probably don't really, oh no, we do use it in some cases, yeah. But the bucket index is going to be the same as its index in this array, because every time we allocate a bucket, we just set its index to where it is in this array and go. And you'll see why this is useful in a bit. And then the count is just how many items are allocated inside this particular bucket. This count on the array is how many items are allocated in the actual array. So you've got a bucket, and then we've got a bucket locator, which is just how do you find a thing in this array, right? For a simple array that's flat, you just need the index of the element, right? And actually, you could do that here because you know the items per bucket. You could have one index and divide and mod, but integer divide and mod are not necessarily that fast. So the approach I took was to take the bucket index and the slot index and put them together into one number, right? Either approach is valid, but this is a little more illustrative of what's going on, I guess. So anyway, if you want to subscript this array, you would use a bucket locator to say, oh, I want the item in bucket 5, slot 3, right? So add buckets, this is a utility function called by the array itself, right? When it needs another bucket because there's nothing left, and we assert that. We assert we better only be here if we're out of unfull buckets, right? I don't want to force the user to initialize this. So if this is the first time we've ever allocated a bucket, that means this is a new array. So we're going to copy our allocator to the, remember these dynamic arrays are a core language type. So we're going to push our allocator onto them if people have set our allocator. That's what happens there. And then we set that up as our context. We go in here, we make a new bucket. Right, this is basically just making that allocator be the default allocator that anyone will call. So any child routine that we call that calls alloc, which is our version of malloc, will instead get whatever this allocator is. And the main place that that's going to happen is in array add here, right? Array add, if it needs to allocate memory for these arrays, which it will the first time you add anything because it doesn't, these arrays don't ever allocate on initial creation when they're empty. So that's why we set up this context, right? So then we make a new bucket, but unlike the C++ new, this new is going to use our allocator that we just set up, right? We set the bucket index, like I said. We add that bucket both to all buckets and to the unfull buckets because it's not full because we just made it, right? And then we return that. So that's adding a bucket. Here I'm not going to go through this because all this does is like it goes through unfull buckets and finds one with an empty slot. So for every bucket in unfull, it had better find an empty slot in that bucket, otherwise it shouldn't have been there in that array. So we sort of assert that. And if unfull buckets is empty, then we just call add bucket, which we just looked at, right? So all this is just finding a bucket and an index in that bucket that are unused. And removing, if we just filled the bucket, then we remove it from unfull buckets, right? And then here's our locator, which we're filling out that tells us, okay, the empty slot is in a certain bucket index and a certain slot index. And then we return a pointer to the data and the locator, because remember, we have multiple return values, right? Because sometimes you might not care about the locator, you might just care about the pointer. So this is stuff to be called by the user, right? If you want to add an item to a bucket array, you just say, here's the array, and here's the item. And we just find and occupy an empty slot and copy the data, right? And that's it. So that's nice. If we want to find an item in the array, here's a locator. This is basically a subscript. I could have called this subscript or whatever, right? So you take the array and the locator, and we find the right bucket. We assert that the slot is occupied, otherwise you gave us a bum locator. And then we return the pointer to that data. I'm always returning a pointer here because you might be using this bucket to store very large things and you might not want to copy it. And I don't want to go down the C++ rat hole of having references all over the place, right? And then here's a remove. So, if you add stuff, you find it, you also want to be able to remove. So that's all pretty straightforward. There's nothing very special there. Now, you also want to be able to iterate over this array. Well, let me see where we are in the demo. Let's just run our demo. Whoops, I'm in the wrong folder. All right. So the start of this demo is just constructing one of these bucket arrays and doing stuff with it and testing it. So we make an entity, we make a bucket array of entities, we add one and we get a locator of bucket 0 slot 0. We add another one, get bucket 0 slot 1. And then we do a find. We'll look at the code in a second, but we do a find and we find the entity data back, and that's all good. And then we remove something from the array and we look at the array. So let's look at the code for that. So here's bucket array test. We're making a bucket array of entities with a bucket size 20, right? And then here's some dummy entity data. You know, it's got an index X, index Y position, and a name. And none of this really means anything. It's just a demo, right? So we're going to add that entity. We're going to say where it is. We're going to change one of the fields just so we can tell the difference between multiple entities that we add. We're going to add that entity. We're going to print that locator, right? And then I'm going to spam 100 entities to add it just to test the creation of buckets and all that, right? Then I'm going to go back and find whichever one locator pointed to, which was this one, because this is where we defined locator, but we overrode it here. So we should be able to find that second entity with index y equals 2. And then we're going to remove something, and we should be able to look at the state of the thing, right? So, so like I said, here's the entity. Here's the second entity's locator. Here's a second entity that we dug out, and you'll see index y is 2, right? Just like it should be because we set it to that here. So we know that we really got that one. And then before we removed, the array had 102 items, right? And sorry for the spam, but this is just the default print. To print out this data structure, I'm just saying print whatever and then array, right? So I'm using the default print for array, which is just where it dumps every field and every value. So some of these fields we don't care about, like we don't care that much about the allocator. But anyway, so before we remove an item, it has 102 because we added those first two and then that 100 and blah, 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 right? Oh, but then before we removed anything, you look at the unfull bucket array. So the full bucket array has 6 buckets, which actually I'm not sure why it's 6. That might be a bug. Why isn't it 5? Oh no, because this is all buckets, sorry, right. So there's 6, so 5 buckets would be 100 items, right? And as soon as we got to item 101, we needed a 6 bucket. So we've got 6 buckets, and that last one is unfull, right? So there's the count in the unfull buckets array is 1, and then the rest of this is stuff we don't care about, right? So now when we removed something, we removed the second item that we added, which is way back in the first bucket, right? So we're going to have 2 unfull buckets now. One of them is just missing 1 item, and the other one is missing a ton of items, right? So that's the relatively simple implementation of this data structure. If you wanted to be very specific about various performance characteristics of it, you could make a more and more involved implementation. So now, once you've built all this, you want to maybe be able to use it, right? Like I said, that's the back-end part of being able to treat your data efficiently, right? Or part of the back-end part. The front-end part then is how do you use it easily, right? So one thing that you're going to do from the user level is you want to be able to treat it like an array. So I want to iterate over this array. So here I'm going to come back, because that array had 102 items in it. If we iterate over it and then do anything like printing, it'll get messy. So I'm going to make a new array. It's got a bucket size 20, but we're just only going to add a couple things, right? So again, this is going to be an entity, but it's got different indices and whatever. So I'm going to add it to this new array and print that locator, and I'm going to set index y to 66 and add that, and set it to 77 and add that. So we're going to have 3 things in here. So now that's this part of the code that we're down to, right? So bucket 0, slot index is 0, 1, and 2, so that all makes sense. And then we're going to iterate over everything and just count how many things. So I made these functions called iterator make and iterator next, where you say iterator make to sort of give you whatever this data structure state needs, whatever this data structure, which happens to be a bucket array, needs in order to keep its iteration state, right? It's just a very small struct that we'll look at in a second. And then I'm just going to count every item. So I'm going to set count to 0. And I'm going to call this iterator next, which is going to give me back the next thing, which I'm going to ignore because I don't care about the values. And if we're done, then this valid will be false, right? So then we break. If we're not done, I'm just going to increment my counter. And my count here that I get from this should be the same as what the array thinks, right? If I iterate over the array, I should get back as many items as are in the data structure, right? And so you'll see that it is, right? It's 3, which is how many things I added. Now, what I decided, right, was that just because you're defining a higher level data structure like that doesn't mean that the language features shouldn't work for you. So just like in some languages like C++ or D or whatever, the built-in for loop in the language can now operate on your own data structures, right? So here I'm doing a for loop over this bucket array, and I'm just going to print all the items, right? And so this one very simple line here, for array print blah, 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 dereferencing it, where it is the name of each element in the array, gives us this, right? So we have an entity, index y is 55, 66, 77. So those are the 3 items we added. In the order we added them, because the bucket array doesn't ever reorder things. Now, just like any for loop, if you don't want to use it for the default name, you can rename the variables, right? So here I'm doing the same thing, but I'm calling the element e and the iterator, right? And for the array, I'm going to print the locator, which is, remember, the position in the array where each thing is, and then the entity data, right? So that's this version down here, where here's the locator, bucket 0 slot 1, 2, 3, and then here's the entity. So this is pretty nice. I don't have to think about what data structure that I'm looking at, and I can just use the built-in for loop to iterate over it. And to emphasize that point, let's just go, if you remember from last time, we had this hash table that we also defined. It had some similarities to what we're doing today. It was also sort of a, did its own memory organization a little bit in addition to hashing data so you can find it quickly. And so here's that hash table again. It's a totally different struct. And here's all that ways that it allocates and expands and stuff. And then we also defined iterator make and iterator next for that hash table, right? And these 2 routines is all that this for loop needs, right? If you look at like the C++ version of using a for loop on your stuff, it's really kind of bogus. You need to define like 4 or 5 different things, and there's like a lot of boilerplate BS that you need to do. And the abstraction is weird, like because they were trying to do this, like iterators in C++ are trying to be a parallel of like the I equals 0, I is less than n, I++. You have to like make a sentinel item, which may not even make sense for your data structure. Like you have to have an end item and a begin item. You may not know what the end item is. It may not fit your current paradigm for what your data structure is. So in this language, I decided to make it as simple as possible, right? There's 2 things that you ever need to implement for an iterator that the language understands, right? You make the iterator, and it's often a very simple thing like this. This is just a data structure with 2 items. What's the hash table and what's the slot index, right? That's it. You make the iterator and you increment the iterator, or you go to the next item, right? That's it. And this will return false if there's no next item. And so you don't even need to know in advance how many items there are, or you don't need to introduce this conceptual weird end item that's outside all your items. You just go to the next one, and if you're done, you're done. Now, if you look at this, let me go to the bucket array one as well. You'll notice these are both very simple. So here's the bucket array iterator. Again, it's just here's the array and then the locator, right? No BS, nothing crazy, nothing extra. And then again, our functions are no BS either, right? So when we make an iterator, we're just saying, hey, it's the kind of bucket array iterator that iterates over this kind of bucket array, right? Remember? So we match this with polymorphism, right? And we say there's the array, and the locator is already going to be initialized to the default locator, which is 0, 0, so we just return that. Boom. No BS, right? And then to increment, we just say, hey, while we're still in the valid range of buckets, we increment the slot index, and if it's occupied, we return, otherwise we keep looping, right? And if we're done, we return null and false, right? So that's it. That's all you need is 2 routines to integrate with the language native for loops. So, again, here's the bucket array version, here's the hash table version, and to go back to the demo, we now iterate over hash table here. So we're going to make a new hash table. This is the same hash table as last time. It's going to be a mapping from string to float, right? String is the key, float is the value. We're going to make a hello bound to 11 and a sailor bound to 69,105. And then we're just going to iterate over the table, which is something we couldn't have done last time because we didn't have these iterators. And we're just going to print every item in the table, right? Now, it's again to be emphasized, this for loop usage is syntactic sugar. You can always go back and do this while loop form if you want. But what this does is it presents a common interface. So you don't really have to think about that much what data structure you're iterating over. You just do it. And we'll talk about why that's useful in a bit. Right, so let's just look at the output there. So table, slot 16. Remember, a hash table drops stuff into random slots. That's why it's fast, right? So first of all, we're getting these back in the opposite order, right? Remember, we put hello in first and sailor in second, but we get sailor first in slot 16 and hello in slot 26. And that's just because hash tables are about scrambling stuff up and putting them in random places. So there we go. We just iterated and printed, right? Now, there are 2 things that are important about all this that I think are very useful for gameplay code. One is the fact that this stuff is strongly typed, right? So my bucket array, for example, knows it's an array of doors, or it knows it's an array of humans or whatever, right? You don't have to get into that low memory C-style management where, in C you might say, okay, I know what the size of a human is, so I'm going to make a thing that's size of human times whatever, and I'm going to use some macros to like cast the result to pointer to human when I get something out of this array, right? Those macros are ugly and they cause problems and your debugger doesn't understand them and all that, right? So here we've gotten rid of all of that. The second thing is my iterator, because I'm allowed to tuck my iterator under this nice cosmetic thing, it's just it's a way of letting the iterator take care of complexities for me, right? So there weren't any real big complexities in those 2 iterators we just looked at. They just knew how to go across a hash table or a bucket array. But for example, in all games that I've ever worked on, you have this kind of conundrum of how to treat entities because in the middle of a frame sometime, you often want to destroy an entity, like the entity exited the world or it got blown up or whatever, right? And if you start messing around with the data structures right then and there, then you might be messing up some people above you in the call stack who are iterating over those arrays or something, or have some state of those arrays that they're depending on. So the pattern that I've fallen into after 20 years, or very early actually in the 20 years of game development, but that's worked for me very well since then, is that destroying an entity just sort of marks it as destroyed and puts it as in a list for bookkeeping at the end of the frame. And then at a known time in the frame, you go and do all your manipulation of all the arrays to take the entity out of them, right? And that means that you won't do any surprises on anybody trying to iterate over those arrays. But it also means that if you iterate later in the frame after that entity has been destroyed, you're going to see the destroyed entity, right? So you could make your iterator for one of these bucket arrays know what the flag is for whether an entity is destroyed or not, and just automatically skip destroyed entities, for example. And that's not that big of a surprise, right? That's something that you can do in any relatively high-level language, but here you can do it with no fuss, and unlike C, again, you don't have to use weird macros and stuff. So in the witness, which we didn't even have C++11 when we were doing this, because we were in an earlier version of Visual Studio. We ended up having a macro that you would use anytime you would iterate over a certain entity type within a certain entity manager. And that thing ended up having an if built into the macro that would skip that element if it was deleted, right, or destroyed. Now, the thing about that is you might forget to use that special version, and you might use the general iteration scheme that you would iterate over any array of anything, in which case you'll accidentally see these entities, right? So, and we went back and forth between different ways of trying to handle this, and anytime you do that on a team, people get confused and remember the old way or get confused about the new way or something. So these complexities happen, and this is a good way of knowing that you're doing the right thing, right? Like whatever is exposed as the standard iterator for the for loop is obviously the thing that you as the user are meant to use, right? You don't have to remember which thing to call. And so that's what I like about this. Now, for all this to have worked, right, my two routines here are iterator make and iterator next. And note that I have one of those on a hash table, right, and one on a bucket array. Which means they're overloaded because these are both, I'm pulling both of these into the same namespace, right? So in previous demos, we did not have compatibility between polymorphic routines and procedure overloading, but now we do. Now that all just works. So the last part of the demo today is just showing that that works. So here I've got a routine foo that I've got 5 versions of, right? Here's one that takes an int. Here's one that takes a string. Here's one that takes some type t, and this is polymorphic, right? But it's got the restriction entity, right? So this t has to implement entity somehow. So the compiler actually checks this type restriction. This one checks, implements hash table, and the compiler checks this restriction. But this one is any type t at all. And remember these modify procedures that we have where we can go into a great amount of detail about what particularly we want to accept, and we can even change the types in the middle and return and cause our polymorph to be different types than what the user inputted. This one just looks like it should accept anything, except it, this code has to run to determine the acceptance or rejectance of the call. And all of that just works. So down here is the last part. We're calling foo on a 5 and a hello and an entity and a hash table, right? We're just printing we're not doing anything exciting in foo. We're just verifying that the right thing got called. So the hash table and then a procedure, right? This modify function is just trying to accept something that's a pointer and then making sure it's a pointer to a procedure. This is something you can't totally express in the base type system of the language because there's no general type for like any procedure because you don't really want there to be, because usually the way you use a procedure value is to make sure you can call it, right? And for calling things, you want strong type checking. So to say that something is a procedure with no further information about its type is not really useful for day-to-day programming because you can't call it ever. So what else are you going to do? But if you ever found yourself wanting to do that, right, then you could verify that this function only takes, something that's a pointer to a procedure, but we don't care about the type of the procedure, right? And you can statically verify that at compile time, right? So like I said, this modify thing is very, very powerful. Well, modify combined with the runtime type information, right? So, down here, I take a constant, right? Bucket array test is that first function that we called to do the basic bucket array stuff. And I'm just putting it into a local variable so I can take the address of it. Is a little, like a pointer to function doesn't quite mean the same thing here as it does in C++. Like in C and C++, all function addresses are function pointers, but I don't see a point in that because you're not going to dereference it except to call it. So, in this language, and it's been this way since the beginning, procedures that you can call are not pointers to procedure, they're just procedures, right? So taking a pointer to a procedure is a little bit of a weird thing that you wouldn't normally do, which is why I'm going through this little bit of acrobatics to do it, but I just wanted to have something sufficiently complicated in here to test for. So, now for all 5 of these, what happens? So this polymorphism and the overloading have to both get resolved, right? Like, so when I call foo of 5, I don't, well, the compiler knows very easily that 5 is not a string, right? But it's certainly an integer, and it might be this. So the compiler actually runs this code for foo of 5 and determines that 5 fails this, right? And the way it does this is it knows whether it's trying to run the routine for real or not for real. To demonstrate this, here's a version of running this for real. I'm just going to copy this procedure and call it foo bar, right? And I can say foo bar of 5, and this will fail, hopefully, right? Yeah, and the way it fails is by running my code, right? And the code says this procedure only takes pointers, line 387, right? So that's here. This error is generated by this modify proc because the thing that I passed has a type T, which is not a pointer, right? So this is totally what you would expect. This is totally covered by previous demos. Now the thing is, because we're speculatively figuring out if we can call this thing, we call it in like a silent mode where errors are not errors, right? I could have forced the user to check whether we're in silent mode or not, and either output an error or not, but I said for today's demo, at least, screw it. If you report an error, it doesn't really get triggered as an error if we're just speculatively deciding if we can call this thing. Now that's similar to a thing in C++, but much, much cleaner. In C++, when you're doing like template substitution and trying to resolve what's going to happen, there's this thing called substitution failure is not an error, which is just banana nut balls in terms of how complicated and crazy it gets. But it's sort of the way that you could speculatively like make things happen. And yeah, in this case, the speculative part of this is clearly delineated. It's only in this block of code that's in the modify. Once I've passed this modify, even if I call other polymorphic stuff from the body down here, once I've passed this modify, we assume that we're valid. So if we make a mistake in here, it's really a mistake, right? The problem with templates in C++ is as you compose them more and more, it can be harder and harder to find out what's really the source of your mistake. Whereas here, we have a much harder line. I don't want to rat hole on that, but I feel like I haven't explained it sufficiently. Maybe we can get into it in the Q&A. Yeah, I feel like I just kind of rambled. Is there anything else that I can say about what's going on? Oh, let me just show that this is running for each of these. So I'm going to go into this modify proc, and I'm going to print we are attempting a modify for something of type, whatever type, right? And I'm going to say t.type. So when we call this with an integer, we should say we're attempting a modify for integer. When we call it with a string, whatever, right? So here we go. Now all that happens way up here at the top, right? So we're trying that procedure for all these things. You know, for the integer, for the string, for this struct. Entity and hash table are both structs as far as the runtime type information cares. That's why we have 2 structs in a row. And then pointer, where's the 6 pointer coming from? Oh, the 6 pointer is when we actually call it, I think. Because, you know, this isn't checking whether it's speculative or not. So this routine gets run, you know, for each of these, but it fails for all of these, which is why we don't end up calling this version when we say foo of hello. We end up calling this version. If we accepted string for this, let me do this experiment. I didn't test this, right? But I could say if t is equal to string, just return, which you'll accept because we're not throwing an error or changing the type to null. So this should accept string, which should then give us an overload error because we've got 2 versions of foo that take a string. Let's see if this works. I didn't test this, and all this functionality is super new and coming in hot, so who knows what's going to happen. But oh, Sorry. This is a type info. I got to do it this way. You know, as of the last demo, when I have first class types, you know, sometimes you do things with first class types and sometimes you do it with the enums and yeah. Okay, so here we say, okay, now there's multiple possible overloads, right? For foo of hello, we don't know which one to call. We have one at line 338 and one at line 350. So line 338 is this one that takes a string, and 350 is, whoops, this one that takes a $T, right? And if I comment this out again, there we go. So again, it's very powerful. It's very unambiguous. It's very clear to track down your errors. And I like it a lot. But it's also early days, so we'll see how it goes. And that's the main functionality I wanted to demo today. Just two things, right? The iterators and the polymorphism working with overloading. And oh, the last thing I want to say about that is, again, unlike C++ templates, this is just a regular procedure, just like this stuff. Like there's a version of this floating around that's like, I don't know what the types of the arguments are. But that's just a more general version of a regular procedure. So anything you can do with a procedure, you can do with this, right? It's not a weird thing that only happens in certain contexts, like in C++, which is what makes it great. So that was it for today. Next time, I want to get more into the details of the particular game that I'm building, but I wanted to just lay this out as a little bit of foundation. And I'm going to take a break for a couple minutes and get some water, and then I'll come back and we'll do questions and answers. Someone's asking why not stop, actually, before we go to question and answer, someone's asking why not stop checking overloaded functions on first success instead of checking all possibilities? The reason is because you want to know when people made a mistake. You want to tell them, right? You don't want to just randomly, if I just write this procedure and think that this should be the one that's called for a certain line, but you're actually calling this one, if they're similar enough, I might not know, right? I want to know what the hell happened. So the reason that you check things at compile time is to catch certain classes of error, and I believe this is firmly within that class of error that you want to catch. Okay, a couple minute break and I'll be back. Also, actually, one more comment on that is if you stop at the first one, then the meaning of your program depends on the order in which you typed it, which is not that great. And actually, in this language, it compiles things a little bit out of order. So you almost could end up in a situation where, depending on what order the compiler decided to compile things, you would get a different version, which is really not so hot. It's easy enough to determine which one is lexically first in the program, but it's just bad beans. You don't want to be doing things that way.